AI floods our media feeds every day. But what innovations are actually spurring it forward? We recently announced Zettascale OCI Superclusters that delivered unprecedented bandwidth scale, ultra-low network latency, and resiliency tuned for our AI workloads. Hello, everyone. Welcome to First Principles. I am Pradeep Vincent, Senior Vice President and Chief Technical Architect at OCI. Modern-day Gen AI workloads demand a substantial scale and have different workload patterns and drive a different set of engineering trade-offs than traditional cloud workloads. That is why we have designed a purpose-built Gen AI network tailored to the needs of best-of-breed Gen AI workloads, and we have been busy innovating on behalf of our customers. Joining me for the third time to discuss some of the key engineering innovations in OCI Cluster Network is Jag Brar, VP and Distinguished Engineer at OCI. Welcome, Jag.
Thank you, Pradeep. Happy to be here.
Well, Jag, we love having you here. So as a third-timer, you just got admitted to a First Principles Hall of Fame that I just made up on the fly.
Excellent. Yeah, I'm happy to be in the Hall of Fame, yes.
All right, so Jag, the OCI Cluster Network has been around for a while, and we recently announced that Zettascale OCI Superclusters with more than 131,000 GPUs. Mm-hmm. Can you talk about how we built the cluster network for Zettascale GPU clusters?
Absolutely. So as you're well familiar, we started on this journey of cluster networks years ago. And cluster networks really is the undergirding bedrock or a backbone for our cluster offering that AI ML customers have come to rely on for training, inferencing, all kinds of workloads. Zettascale superclusters are about much larger scale, in particular scale that offers up to 52 petabits of non-blocking bandwidth for the entire cluster and hosts attached at 400 gigs with latencies as low as 2 microseconds. 5 times the scale and 5 times lower, 5x lower latency that another hyperscaler has announced for their large clusters. So it's pretty groundbreaking, I would say. But in the end, it still relies on the same principles we've used for our cluster networking all this time. So we went from 512 GPU size clusters to a few thousand, 16, 32,000, 64. Now we're at 128K, which is 131,072. Not only does this cluster network supports these large clusters, but it does so at line rate throughput for each of the GPUs. And it includes innovations along the lines of making RDMA scale at really large scales, at really low latency and very high workload resilience. And then also doing advanced new forms of traffic load balancing, something we call collectives aware load balancing. It took innovation in every area of networking that we touch.
So why did we choose RDMA in the first place? And what improvements have we made with it that has made it possible to scale so much?
Yeah, so RDMA, turns out when we first went down this journey, we started with the Oracle database because Oracle database needed RDMA. And really the essence of RDMA is to get CPU bypass and kernel bypass to get high throughput and low latency, which turns out is very useful for HPC applications as well, which we offer, and in particular for ML workloads. They really can use all the bandwidth you could give them. So they're very bandwidth hungry workloads. And so RDMA is almost required and perfectly suited for
our database service is certainly one of the most demanding workloads.
Very demanding,
clearly,
exactly.
It's one of the top-notch services we have.
Exactly. So, and in order to make RDMA work at scale, we needed a technology that could have RDMA scale at the scales we needed to, and that is RoCE. In particular, what's called RoCE v2 or routable RoCE. And our RoCE journey is slightly different than maybe others, which is we wanted to shoot first for really large scale. Our goal is arbitrarily large scale, and that comes down to using principles of distributed computing and distributed networking. This is our design philosophy, and that comes down to loose coupling in the network. So the network isn't brittle, isn't too tightly coupled. And as an example, previous attempts at RDMA using Ethernet, so RoCE, relied on this protocol called PFC, Priority Flow Control, which is a way of doing link by link, and in the end-to-end link by link flow control. And we found that that was not the right way to go because it doesn't lend well to these distributed principles of distributed computing. So we went with not relying on PFC and instead relying on congestion control. So as opposed to blocking and stopping when there's congestion, congestion control slows down and waits for congestion to go away and then picks up. And it turns out that is the right trade-off because it allows us to scale. So we use PFC as needed at the very edges of the network, and for the rest of the network, for the entirety of it, we use congestion control as the primary mechanism for performance.
So it's more of a modular approach, so
It
that
is.
it's not that tightly coupled, so that you can keep scaling it.
Exactly. So scale was the key property we wanted to shoot for. And while we're at it, we also solve some other sort of neighboring problems, as in we're a cloud provider, so we're serving many customers. So we want security isolation between customers, which we achieve using network virtualization, which was new. Nobody really had done that for RDMA. And then also we wanted performance isolation across customers, because RDMA and Rocky is all about high performance. And we achieved that using building a very sophisticated QoS-enabled network where each class of traffic, HPC, Oracle database, ML traffic, gets its own queue, its own lane in the network, which is tailored for its particular requirements for performance.
Essentially, we kind of separate out different classes of workloads so that they can be treated separately.
Correct.
Is that right?
Yeah, and that they get exactly the treatment they want.
Yeah. What other things have they had to do to address Gen AI specific requirements?
These workloads, when they run, all the GPUs their NICs are pegged. It's actually running at line rate. So line rate these days is 400 gig and soon to be 800 gig. So all the NICs are pegged. So we're talking about line rate throughput at the scale of this cluster, which is humongous. So, and our goal is arbitrarily large scale. That's what we want to achieve, and we believe we can. So we had to innovate in a few ways. The first one being, when customers get clusters from OCI, we have a notion of a control plane. So there's a long-standing control plane that customers have used, or under the hood they use to launch instances. Similarly, when you launch your GPU instances, the control plane does its best job to co-locate the GPUs as closely as possible to each other. And that has a few advantages. One obvious advantage is that it gives you lower latency because they're nearby, cable distances are short, you have to go through fewer network hops. But the other advantage, it gives you higher throughput. And that's because traffic not having to go through more switches. And so the first lever we have is control plane being intelligent of placement. The second is this service OCI we built called the Network Locality Service. This is a service that advertises network topology information and placement of customer GPU information about that to the customers. So now if you're a customer, we tell you what our topology looks like, and we tell you all of your GPUs, given the topology, where do they sit. Now what you can do is you can use hooks that are currently available in schedulers and libraries, GPU ML libraries like Nickel, for example, or RICL, to make use of this topology and get high performance. So that's the second lever. And thirdly, we have relied on advanced forms of traffic forwarding. It's called load-aware traffic forwarding, load-aware ECMP, that gives us performance advantage. And since then, we have actually worked with one of our vendors to innovate on a new kinds of load balancing technique that also gives us another lever for performance, and hopefully we'll talk about that shortly.
Clearly, there's a lot of things going on behind scaling the bandwidth, if you will. But let's talk about latency. Mm-hmm. So you said we achieved 2 microseconds of latency. That isn't a lot of time to process any network packets. Mm-hmm. It's certainly not not enough time to do memory lookups. Even if it's high-speed memory, you really can't do memory lookups as part of packet processing. And even light actually takes 5 microseconds to traverse a kilometer of optical fiber. So how do we achieve this type of network latency? Did we just find a way to break speed of light, Jag?
No, so no, we haven't.
Shout out that.
No, we haven't made any breakthroughs in laws of physics. Fundamental sort of levers we've used to achieve low latency is, the first one is to control cable distances. For example, you mentioned speed of light latency in a kilometer fiber is 5 microseconds. So we want to try and do our best to limit the cable distances, and we certainly do that. And so we have very clear specs on what are the cable distances throughout of our network. So if you look at our typical network topology, it's a 3-tier, what we call CLO network, where there's 3 tiers of switches, tier 0, tier 1, and tier 2. Each switch, for example, a tier 0 switch, serves a certain number of GPUs, right? So a tier 0 switch typically serves like 256 GPUs. So if your workload fits in those 256 GPUs, your latency is going to be 2 microseconds. Now let's say you have a larger workload. Let's say you need 1,000 GPUs. That would fit in what we call a block of a network, which is within a set of tier 0 and tier 1 switches. And for that, you have an extra couple of switch hops. You go from GPU to a tier 0 switch, to a tier 1 switch, to another tier 0, to the target GPU. That's about 5 microseconds. And here we're talking about one-way latency. So latency generally is defined as one way, whereas round-trip time is both ways. And then if you have a really large workload, let's say 130,000 GPUs, then we'd have to go up to the second tier, and that is 8 microseconds of latency. And the reason for that is extra switch hops and also extra fiber distance. And we strictly limit the actual fiber distance for all layers of the network. And not only do we limit it, we also control the minimum. So we want to avoid variation in latency as well, which is another side property.
Consistency.
Consistency. That's the right word.
Yeah.
So now if we were to look at, you asked about memory lookups. So all of the infrastructure, NICs and switches, they avoid either DRAM lookups or even HBM lookups, because as you noted, that can be very slow. Generally, all of these lookups are either in TCAM, which is ternary content addressable memory, very fast, or SRAM, which is also very fast. This is on-chip memory, which is much faster than DRAM and HBM. And now if we were to look at latency for, let's say, the smallest diameter, which is the tier 0 switch, going from a GPU to a tier 0 switch to a tier 1 switch, you would go from GPU to the NIC that's on the GPU, that the GPU is next to a transceiver that's on the NIC, then a cable, again, fixed distance cable, to a tier 0 switch that will have its transceiver in front, through the transceiver, through the switch, and then through another transceiver to the other GPU. And each one of these components have a latency budget, so to say. Transceivers typically consume about 100 nanoseconds of latency, and it has to do with things like forward error correction codes. Similarly, switch has a switching latency, and that's the latency a switch incurs to do a packet lookup, to do any packet munging it has to do, any buffering, any scheduling. So that's about 900 nanoseconds. And then cable distances are limited, and you consume about 200 nanoseconds on either one of these cables. Add all that up, you get to 2 microseconds unidirectional. For show and tell, I brought...
we got props.
Yeah, props.
First time ever.
Exactly. There we go. Here's a transceiver, not unlike the transceivers we use in our network. It has electronics and a laser on it. There's photodetectors for detecting received light, and it consumes about 100 nanoseconds of latency. Some of that latency is because there's digital signal processors on the transceivers to do modulation handling and error correction, and there's a forward error correction code that also consumes a few nanoseconds. That's about 100 nanoseconds on a transceiver.
So now that we talked about scale of bandwidth and latency is essentially how a network is built, let's talk about the resiliency part of it. Performance of AI ML workloads generally tends to be very sensitive to any form of disruption, including network disruption.
Yep.
Even a small disruption can have a really outside impact on the workload performance, right? So what do we do to help Gen AI workloads do better?
Gen AI ML workloads are actually more sensitive to these interruption, disruptions, events in the network than, let's say, typical TCP applications. Unlike typical TCP applications where there's a notion of a client-server paradigm, there's a load balancer or level of indirection in the middle, that's not the case here. These are very tightly coupled workloads where GPUs are talking to almost like in a peer-to-peer model where everyone's dependent on other people's work. Or you slow the entire workload down. So the impact of a slowdown is felt at the scale of the workload. That's the first observation. The second observation is these workloads are more sensitive to the impact because of the fact that the transport that's often used for RDMA doesn't quite have the same level of reliability is probably the right word, kind of like TCP, where the impact of small amount of packets lost is felt more, is more obvious than it's for TCP. TCP masks a lot of packet loss from you. In fact, TCP expects loss for it to do congestion control. Unlike that, congestion control in RDMA networks is slightly different, where it senses congestion and avoids packet loss. So if there is packet loss, there is a bigger impact because there's a lot more packets that need to be retransmitted.
Yeah.
So we have had to do a lot of new things. The fact that transport is sensitive, these workloads are so tightly time synchronized that
That's the unique part.
Yeah.
RDMA has been, has always relied on lossless network. It's
Yes.
always been sensitive. But this giant clusters essentially have massive synchronization across them,
Synchronization.
right?
So if one leg or one unit slows down, it slows down everybody
Right.
else. So that makes it even more of a problem.
Exactly. To the extent when we actually see, network blips, we actually see the power go down and up.
Exactly.
Which is really odd.
Yeah. Power draw is a proxy for events in the infrastructure. And there's one other thing which is relevant for the reliability of the workload is that the sheer scale of these workloads is so large. Now we're talking about 100,000 plus GPUs that all have to be working and chugging along as fast as they could at the same time, that the probability of some event happening is higher because the scale is larger. So that's the next factor. So what that meant is we really need to do our best to offer the highest possible reliability for the customers. We've deployed these techniques to make the links, the optical links, be more resilient to temporary disruptions. And the second is we actively monitor all links, switches, transceivers, and look for events that we could then project from. And if we have a transceiver that we believe is not performing the way we expect it to, that it could fail in the future, we could predict and do repair on it proactively, as opposed to it actually failing. And the next is we have automation systems that look for repeat offenders. Imagine if you have a link that failed twice in a day, as an example. So we'll look for that, and we proactively take that out of service, drain traffic off of it, and initiate repair activities. And then lastly, we have an agent that runs on customers' GPUs that monitors environmentals, performance of the NIC, anything that is worth pointing out to the customer that they may want to initiate repair activity on their end. So help them monitor and look for potential problems.
Got it. That makes sense. So you mentioned, that temporary disruption or link flaps, if you will. What are some of the causes of link flaps?
This is a topic very near and dear to my heart. So basically what's happened is, as networking world has evolved in speed of the links, it used to be 10 gig, 100, 400, now we're at 800. It used to be the case that previous generation of links used what's called NRZ encoding, which is non-return to zero. So you either have a laser on or off, that'd be 1 or 0. To get higher speed links, we moved to this technology called PAM. PAM4 specifically, that stands for Pulse Amplitude Modification. And the idea is you have more than one level of intensity of light, amplitude of light. That means now the signal to noise ratio for the signal is lower. So that means your reach of the signal is less. To gain reach, the industry went on to use these things called forward error correction codes, which is basically adding extra information in the packet, because you expect bit error, so you can correct for it. So all that works well, and that's what makes 400 gig and 800 gig possible. What we've observed is that because these technologies are more complex, perhaps that is the case, or just the sheer scale of these clusters are so large, these networks are so big, that the probability of a link experiencing a problem is higher. And the IEEE spec for 400 gig, 800 gig links is very stringent in that, since it expects bit errors that forward error correction can correct for, there could be cases where the FAC cannot correct for the bit errors.
Uncorrectable errors.
Uncorrectable bit errors. So the spec is very tight in that it expects no more than three uncorrectable bit errors in 3 what's called code blocks, 3 sequential code blocks, which is, in theory, that could happen in 20 nanoseconds. Within, let's say, less than 50 nanoseconds, you can, in theory, have 3 uncorrectable bit errors. Now, that in itself may not mean anything, but the issue with that is, when that happens, what you're supposed to do is you're supposed to take the link down. Now, that might not seem like a big deal, and for TCP applications, it probably isn't. But for RDMA applications, it is. Because what happens is, when you take the link down, let's say the link is down for a millisecond, which can definitely happen, like if this 3 bit errors was to happen, and the link was to be brought up, you could do at the optical layer, let's say, in a millisecond. Because of the fact that it isn't just the optical layer. So, if we were to look at the various layers of protocols that are built one on top of the other, if you just look at the physical and the data link layer, there are multiple layers. At the very bottom is what's called the PMD layer, right? That's the media dependent layer. That is the laser we're talking about and the photodiode. So if there is let's say, 1 millisecond interruption there, 3 bit errors that are uncorrected, the link bounces, all of the layers above it, the PMA, the forward error correction layer, the PCS layer, the reconciliation sublayer, the MAC data link layer, all of those layers have their own inbuilt stabilization routines. Some of those are heuristics, where you wait for a certain amount of time, you wait for certain bits before you call that layer to be reliable enough. And that all adds up. And what we observe is that one momentary optical event could end up being a 10 to 15 second link outage. And that is simply too large.
All the way up to the routing layer.
All the way up to the routing layer. There could be an event above the routing layer or inside the routing layer, because you now have to update the entire network. There's routing convergence. And that will happen twice. Once you take the link down, and then second time when you bring the link up. And we feel that for AI ML workloads, that's unnecessary for a very small, momentary, once unrepeated event. And what we feel the right thing to do instead is to not take the link down, to let those packets be dropped. Because the packets would be dropped anyways, regardless. And in fact, they'd be dropped for longer. Drop the packets, don't take the link down unless that event happens again. If it happens again, then we do the repair activity. But if it just happens once, it's a once in a lifetime event for that link. We see two classes of failures. One is actual genuine failures, where the thing is bad and it is going to fail. Even if you ignore that 1 millisecond outage, it's going to fail again. And then you have the answer. You just replace that, right? You do the repair activity. The other classes, which is not uncommon, where there's just this one event for some reason and it never repeats.
That's the key. It seems to be, it's not an indication of actual failure.
Correct.
But yet it's not, completely rare.
Exactly.
It does happen.
Exactly.
Right? And what are some of the causes of that type of transient failures, if you will, or transient link flaps?
So if I were to bucket the issues, the first bucket is actual genuine problems like dust on the transceiver, poor quality of fiber can happen, actual genuine manufacturing defect on the transceiver. And then there's the other category, which is non-repeating offender, right? Once, there's an issue once and it never occurs. And that could be a transient temperature issue. It could have to do with a transient airflow issue. There does remain that non-zero probability that there are some links that will occasionally have a flap and never again. And the other reason that we are so interested in this link resilience is that imagine this issue was to happen not between two switches, which is one case. The other is, let's say, it was to happen on the NIC on the GPU. Now what will happen is if you take the link down, the worst possible outcome is the workload could crash. And if workload crashes, because it can crash, it depends on the actual application. If the workload crashes, somebody now needs to get involved. And you now need to go back to the previous checkpoint, and you've now lost a lot of time. So there's a high price to be paid for not having link resilience.
For transient link flaps.
Exactly.
Yeah. Okay. Sounds good. So, what are we doing to mitigate the impact of these transient link flaps, if you will?
So basically what we've done is we've instituted what we call link stabilization or link debounce, both on the NIC and on the switches, where if there is a momentary once flap, not a repeat flap, we keep the link up, we let those packets be dropped, and then congestion control will do the right thing, which is it'll retransmit. Yes, it'll retransmit some extra packets, because that's the state of the art of the congestion control and RDMA transports. But it's much, much better than dropping packets or losing capacity for 10 to 15 seconds and, God forbid, crashing the workload, right? That's what we really want to avoid.
Well, but did you say that we are actually going to keep the link up and actually drop some packets?
Correct.
For a transient period of time?
Yes.
But isn't RDMA super sensitive to packet drops?
Very good point. It is the case that RDMA transport is significantly more sensitive to packet drop than TCP. But it's not that it cannot accept any packet loss. It can handle packet loss. There is a notion of retransmission. It's just that the retransmission window is larger. That's one issue. The second issue is that it ends up slowing down the workload, so it doesn't have...
But not crashing it.
Not crashing, right?
Yeah.
It's
so it's a lesser of two evils, right? That's
correct. And then thirdly, thankfully, people have done new work on RDMA transports, and transports have come a long way. And now there is a notion of what's called selective repeat, where if you lose an occasional packet, the receiver NIC can signal to the sender NIC to just send that one or a few packets that are lost and not many more neighboring packets. So transports are also maturing and becoming more reliable.
All right, that sounds good. So, when you think about Gen AI workloads, when there's massive amount of bandwidth being used across a large cluster, there can be scenarios where there's link congestion, particularly in the upper layers of the network, if you will, even in a non-blocking network like the one we have at the OCI Supercluster. How can there be bandwidth or flow collisions in a non-blocking network, and how do we actually manage it?
Yes, good question. So your question is, hey, if the network is not oversubscribed, why is there congestion?
Exactly.
So there are two reasons that network can have congestion, even when it's non-blocking. The first is an easier thing to describe, which is encast. It's a well-known phenomena where a particular receiving host is subscribing to too many senders. It ends up congesting its port, as in its port coming from T0 switch, the first hop switch to itself. So that's a self-inflicted harm. And there are well-known ways of handling that, either using some sort of credit mechanism, or more commonly, letting congestion control do its thing. That is a less common scenario. That doesn't quite happen as often in ML networks. The more common scenario is, if I were to describe, stepping back, what is causing it. So applications, both TCP-based applications, TCP, and RDMA, expect packets to arrive in order. Now, for a network to keep all packets in order, network has to now forward all packets for a given flow being a source host, a dest host, and the UDP ports of the host. They have to maintain all packets for that flow in order. The NICs, they can do that, all the switches. Now, that places a very strong requirement on the network. The switches now have to keep all packets for a flow in order. But switches don't know how large a flow is. Is it a 1 gig flow, or is it a 100 gig flow, or a 400 gig flow?
It's the elephant flow or mice?
Elephant or mice, exactly. Yeah. So switches have to make a statistical decision on how to pack flows on parallel paths, and they often get this wrong. This is the essence of what we call flow contention, where switch makes a mistake, and that causes what we call flow contention, where you put too many flows on one link and too few on the other. So there's congestion because traffic is inefficiently load balanced. So that is something we've worked hard to solve. We've since gone and worked on a new kind of technique in collaboration with one of our vendors that solves a particular kind of problem for a particular class of ML workloads, and we refer to it colloquially as collectives-aware load balancing. Imagine you have two topologies. They're both two-tier close. And in one topology, you use ECMP, which is equal call multipath forwarding, which is standard flow hashing. And the other is collectives-aware load balancing. And the difference is ECMP would do this statistical hashing of flows.
Using like standard 5 tuples or something like that.
4 or 5 tuples. So source IP, dest IP, source port, dest port, and protocol. So that would be the 5 tuple. And it could make a mistake. So if you look at the schematic on the left, shows 2 workloads or 2 set of flows, red and blue. And the leftmost tier 0 switch has made a mistake and put both red and the blue flows on the same one uplink towards the first tier 1 switch. So that has now caused congestion, while the uplink towards the second tier 1 switch is sitting empty. That's the essence of flow contention causing congestion, even in a non-oversubscribed network. Now, the schematic on the right, topology on the right, shows what we call collectives-aware flow forwarding, collectives-aware load balancing. Here, the switch is aware of the fact that this is ML traffic. This is not TCP traffic. Flows are not really of different size. You can make some assumption about the fact that the flows are roughly of the same size. So it makes sure to not pin both the red and the blue on the same link. It puts the red flow on the first link to the first tier 1, blue flow on the second link to the second tier 1, and thus avoids the congestion.
So instead of 5 tuple, it uses the collective metadata itself.
So it looks in the header and determines this is an RDMA ML packet. And then it goes, OK, I'm going to make sure to not overpack the flows on the uplinks. That's the first thing it does, which is to avoid contention at the uplink of the tier 0. It actually goes a step beyond. The second thing it does is it tries to also avoid congestion at the tier 1 going down to the remote tier 0. And the way that it does is, if it has multiple flows from a given IP, so in this schematic, let's say GPU 1 has 2 flows to GPU 3. It would then make sure to not send both of the flows through the same tier 1. Because what happens is other tier 0s could also be sending their traffic to that GPU 3. You don't want all of those flows to then collide on the downlinks from tier 1. So that is forwarding collective severe load balancing.
Well, thank you, Jack. Well, so this has been fantastic discussion.
My pleasure.
I think it clearly shows the investment we've been putting into OCI Superclusters that underpins OCI's AI infrastructure offerings, and that's been serving our customers really well. Thank you for joining.
My pleasure, and I'll put in a plug-in for my team. It's my team's work, our team's work. Yeah, so thank you.
Here are some of the key takeaways. OCI's Zettascale Supercluster redefines network scalability and performance for Gen AI workloads and deep learning workloads. OCI Superclusters deliver RDMA at Zettascale with ultra-high throughput achieved by applying principles of distributed systems and distributed networking. It delivers ultra-low network latency achieved using placement-aware control plane, network locality service, and engineered cable distances and network configuration. It delivers enhanced network resilience by using advanced link resilience techniques and by automating detection and repair of network faults. And it delivers advanced traffic load balancing to reduce network congestion events.